The next topic is dealing with, it's all about trust, simulation credibility. This talk is about the issue of being able to trust in the simulation results, and the speakers will present us the general problem on the one hand side and the possible solutions they found. We would like to start with Anne Grätz. She's from Robert Bosch, cross-domain computing solutions engineering system function. And Anne is a member of work package quality requirements for the simulation platform and requirements for validation of simulation models. Followed by Dirk Frerichs. He's from Opel Automotive, from the division Vehicle Digital Engineering Department, CAE Methods, Expertise and Support. And Birte Kramer, she's researcher and PhD candidate from OFFIS Institute for Information Technology, and she's leading the work package quality requirements for the simulation platform, requirements for validation of simulation models, and quality criteria for coupling of simulation models. And I would like to hand over to you, Anne, in the first place.
So welcome to the session of simulation credibility. In this session, we want to give you an overall introduction in that topic, since model and simulation credibility is a topic that affects different working groups and use cases in the Level project. We prepared a storyline to give you short summaries of the different working results in the Level project and show their interaction. So this is Debbie. Debbie is a simulation model developer. She develops radar models to test automated driving systems. Debbie is an expert in her domain. She spends a lot of time and knowledge designing the simulation model. Additionally, she established certain activities to improve the quality of a model, like verification or validation tests. So Debbie is happy with her model and the time invested. She transfers her radar model to Charlie. Charlie is responsible for testing the automated driving function regarding the safe behavior of the vehicle. Therefore, Charlie wants to use the model to build up a simulation environment consisting of various component models. But then Charlie starts to have doubts. Can he really use the model for his intended use? Charlie knows that Debbie is an expert in her domain and that she builds great models. But Charlie is responsible for the approval of the overall simulation environment. He decides whether the automated driving system can be tested with the created simulation environment. Based on the available information, Charlie feels uncomfortable. There's not enough documentation available to figure out what kind of activities Debbie applied to ensure her model's quality. And it's not clear for him for which intended use Debbie designed the model and which assumptions and requirements she considered for this sensor model implementation. And even Debbie doesn't know how she can best support Charlie in all his questions and doubts. She's not sure for which intended use Charlie wants to use her model. So what about you? Have you ever been in a similar situation like Debbie or Charlie? Do you trust in your models? And why? So Charlie and Debbie are not the only ones who ask themselves if they can trust in the models. If you have a look at the literature, scientific community, or organizations like NASA or the American Society of Mechanical Engineers, there's a thorough discussion about that topic. The term most often used for the activities in this context is credibility. A few selected definitions are model credibility refers to the decision maker's confidence in the model. One goal of the verification and validation process is to gain this credibility, according to John Carson. And credibility is the quality to elicit belief or trust in model and simulation results, according to NASA. So what does the literature and scientific community recommend to reach that credibility? The model developer and the model user must interact during the overall model development and operational phase. It is important that both agree on the purpose for which the model is being built and its underlying assumptions. In order to assess and evaluate the credibility, various criteria are mentioned in the literature. It is important that all activities are documented transparently and follow an agreed procedure. So let's follow our heroes on their journey to achieve the credibility of the radar model.
So let's take a deeper look on the suitable criteria to assess and evaluate the credibility of the radar model from Debbie and Charlie. The main challenge here is to objectify the process of creating credibility and to tailor the validation and verification activities to the specific intended use of the model. The interaction of these so-called credible criteria can be illustrated within the decomposition of the modeling and simulation process. At the beginning of every modeling and simulation process, there's the reality of interest, which has to be presented by a well-defined and developed model for creating resilient simulation models. To accomplish this, a systematic analysis and modeling of the reality of interest has to be carried out, not only for the model developer, but also for the model users and the decision maker to derive the conceptual model. So we can see here that different groups have to come together for these activities. This conceptual model can be defined as the collection of abstractions, assumptions, and descriptions of physical components and processes representing the reality of interest. One part of that could be, for example, a state space model with predefined parameters and corresponding parameter value ranges of these, but not limited to that. The process of determining the degree of which a conceptual model adequately represents the reality of interest from the perspective of the intended use is referred to as conceptual model, which provides the first essential credibility criteria. For example, validation and verification techniques like phenomenon identification and ranking technique can carried out during this step. For deriving a simulation model and an implementation of a conceptual model has to be performed. The simulation model is represented by software code and characterized by ability to be executable for a specific solver tool. To prove if the right conceptual model is implemented, the verification is required as the next important step to create trust into the model. For this, the simulation model has to be complement with the requirements and specification as detailed in its conceptual models. This is the second important credibility criteria. Having the simulation model at the hand, experiments with respect to the intended use can be carried out. Thereby, the process of determining the degree to which a simulation model provides an accurate representation of the real world, so with focus on the reality of interest. So the simulation model is assessed from the perspective of an intended use, which is called operational validation. This builds the third important criteria for the creating credibility of the modeling and simulation activities. This picture is only representing an abstraction of the modeling and simulation process. For making presented modeling and simulation process a bit more specific, an example of an operational validation of a radar sensor model was elaborated within Z-level project. Depending on the intended use, a simulation model needs to fulfill different requirements during the verification and validation process. The NISA standard 7009A for models and simulation follows a level-based approach that allows clear communication about necessary steps during the verification and validation process. In this table, we can see the requirements for a level 0 and a level 4 validated simulation model. In our story, Charlie and Debbie are interested in to reach a goal to achieve a level 4 simulation model of a radar sensor. To create a level 4 validated radar model means that we will compare the developed radar model against measurements the operational validation from the real world or from results from a higher fidelity simulation model. While for a level 1 validated simulation model, the model only needs to be conceptually validated. Thus, there is no need to compare simulation data to a higher fidelity model or the real-world system. This level approach, based on the NASA, is one of concepts discussed and adapted in said level project. How can a sensor model be validated? The validation process shall show that the model is fulfilling the needs of the user. Assuming the user wants to simulate a sensor fusion stage, the sensor model has to provide similar output like a sensor to be replaced. Thus, the validation has to show that the deviation of the model output from the sensor output at the same scenario is smaller than the agreed tolerances. The sensor output is recorded at various scenarios. These scenarios are also defined in the virtual world of simulation. The model output has to be compared against the sensor output in the corresponding scenario. According to the use case of the simulation, the inputs of the model need to be varied over the whole input range. To identify the most interesting sample points for the validation, a sensitivity analysis is recommended to be performed. An examination of the deviation of the output is indicating whether or not the model is valid for the use case of interest. Vierhoff's validation method requires the simulation of the model that way that the quantity of interest in this scenario kept constant. E.g., for example, the validation of the output of distances, longitudinal and lateral scenarios are used in which all traffic objects, for example, corner reflector or pedestrians, including the host vehicle, are in stillstand. This you can see on the table on the top. For the validation of the output of the velocities, the relative speed between target and hosts has to be kept constant. The easiest way is that either the target or the host vehicle is moving with constant speed. To validate the output of one quantity of the range of the output must be sampled several times as shown here in the examples in the table. In the examples, each variation in speed for distance is one configuration sample. For each configuration sample, the output of the model and the sensor is compared and gets classified according to the correlation of both outputs. The results is displayed in the validity assessment map like the one over there. With each release of validated model, Debbie is sending over a report to Charlie, introducing the validation method, the considered test cases, and showing the results of the validation. Together they can agree on the next steps of the model development, and Charlie can decide for which test cases the model can already be used. This validity assessment report is one of the Z-level project's deliveries and will be soon publicly available. So we saw how to perform one operational validation for one single radar sensor. In addition, there are further criteria which can support a comprehensive credibility assessment like data pedigree and uncertainty characterization. Based on these criteria, it is necessary to enable model developers and customers of these models a systematic way to prove the credibility of the simulation models. So the model developer gets the modeling task to create a suitable radar model for a specific engineering task with the predefined requirements. Through the available information, it is predefined that an operational validation has to be performed to assure quality before delivering the modeling and simulation results to the customers. To support the model developer during his activities to assure quality, a library of verification and validation methods and techniques is developed in Z-level project to provide to him. The main purpose of such a library is to guide the developer through the jungle of methods and techniques. The method's main focus is the why and the how, while the techniques focus on the what. The library makes a proposal which methods are suitable to fulfill the corresponding credibility criteria. The suggestion here, for example, is to use the validation method of Michael Vierhoff, requirement-based validation of simulation models. The how. Based on this method, different validation criteria have to be used. If this matches to the specification of all necessary validation techniques are shown to perform to the actual task, the what. Additional roles which are needed are listed. In this example, the model developer as well as a test driver or a physical prototype and or a test bench is required. With all these information, the model developer is guided to fulfill his task, the operational validation of his developed sensor model.
So what we have talked about now are different methods, criteria, and techniques for the verification and validation of simulation models. However, in our application domain, we have to deal with several simulation models. For example, a camera model or a vehicle model that are all coupled in a simulation platform. But what does that even mean when I say coupled? We differentiate between different kinds of coupling. In a monolithic simulation with only one solver on the left side, and a distributed simulation with more than one solver on the right side, as well as monolithic modeling on the bottom versus distributed modeling on the top. We focus on the coupling methods on the top right, as in set level FMI for co-simulation is used, which can be grouped into the right side of the graphic. So in general, one tries to avoid the coupling of methods altogether. Coupling is a potential source of error, and it often introduces delays and further discrepancies from an analytical solution. So we need to ask ourselves, is this really necessary? Unfortunately, the answer is oftentimes yes, because of the high complexity, modularity requirements, and IP protection. So for this reason, coupling is something we do need to consider. The ideal goal would be to identify, quantify, and assess the influence of coupling. To do this, we would need a monolithic system and compare it with the coupled system. However, this is not possible in our application, as model developers need to protect their IP. So we have to think of something else. So what we can do is to generally look at coupling mechanisms and compare, for example, their models of computation, note with information is necessary, etc. Moreover, we can test coupling mechanisms for easier models, where we can actually compare the monolithic system with a coupled system, and then we can try to generalize to more complex models. However, this is work in progress right now, thus more details will be given at our final event. So all these component models are coupled to the overall simulation environment. The overall system model, which with its integrated simulation models, must also pass through the three phases of conceptual validation, verification, and operational validation. But how does this fit into the overall set level approach and process explained in the sessions this morning? All discussed activities right now take place in the modeling layer. The modeling task describes the requirements and objectives that the model has to fulfill. It is derived from the overall simulation task and targets, and this again is derived from the overall engineering task we have to fulfill. After the overall simulation setup, including all its component models, is verified and validated, the simulation results for the concrete simulation task can be obtained. They need to be evaluated, and a decision about the fulfillment of the simulation objectives must be made. This decision provides the necessary information for the engineering task and its decisions to be made. But how can we be guided through these steps? All the mentioned process steps and required artifacts are defined in the credible simulation process.
Debbie applied all the necessary credibility criteria to her model and agreed the requirements and methods used with Charlie. For Charlie, the intended use of the model, the underlying assumptions, and all quality and credibility measures are transparent and traceable. Thank you for being with us and our heroes today on this journey to model credibility. Our heroes have further adventures ahead of them. So maybe we'll see each other again at the final event of that level. Thanks for your attention.
Thank you very much to all of you. That was a very nice way of making us understand something about simulation and trust in results. Julian, I'm sure we have lots of questions. Did you pick one already?
Yes, so the first question goes in the direction of the link between the reality of interest and the validation activities that you described. And the question is like this: often complete realism is not needed for a model output so that the system under test can be tested. So you use a part of the reality that can generate meaningful output so that the system can be tested. How would you validate such a model which is somehow depending on the algorithm under test rather than a fixed full reality that you can use for comparison?
Who would like to answer the question?
So I can answer the question.
Perfect. Dirk.
Or I can try to answer the question.
It's
not easy to give a short answer for this, but we always have to keep in mind, or we have to think about, how should I know that the model fulfills my quality metrics? So how should I know what I need for my tests? And based on this, we have to have a look in the design phase of the model development. So coming from the reality of interest to the conceptual model, which effects do I need to fulfill my engineering or my simulation task? And based on this, I can define, for example, if I'm talking about vehicle dynamics, I can define specific dynamic components which are important for me. And if I want to do a control algorithm for lateral controls, I know, okay, if I need a model for this, I have to develop a simulation model for my use case, which represent my lateral attributes of my systems. So based on this, I have to separate my complete system and make a decomposition into the components parts that I need. So I hope this answers the question a little bit.
Thank you.
I assume that it did. We have still a few more minutes left, Julian.
So we have another question, and this goes in another direction. So there are some activities about credible simulation framework, for example, in evaluation instances like NCAP. So the question is, do you consider some interaction with Euro NCAP to discuss your approach with such assessment bodies?
Who would like to answer?
Would there be some interaction possible, do you think, or?
Yeah, I can try to answer. So I think, yeah, we should interact with those organizations and standard approaches. And since we referred also to the credible simulation process, I think we have a good chance and a good opportunity in that level with the credible simulation process to yeah, interact with those organizations and bring our experiences regarding those standard approaches to those activities.
Thank you, Anne.
Okay, if we have time for a last question.
We do indeed.
In the example that you showed, the focus is on the validation and verification or the use of the quality attributes on a model. Do you plan concrete activities on the model above, so at the simulation model where all at the simulation level where all the models are integrated?
So I think that's a question maybe for me. So yes, we actually do, but we plan to derive quality criteria for the coupling methods, and then maybe try to use them in the verification of string of of our triangle, and yeah, but this is work in progress right now, as I already said. So hopefully we will have a better answer at the final event. So, yeah.
Thank you, Birte.